All right, so we're going to go ahead and talk a little bit briefly about distributed networks. So let's share the screen. All right, so the main thing to think about with, oh, is that going to work? Main thing to think about with networks is that there are a lot out there to networks, right? So the statistical modeling of networks is really trying to figure out how you go from this one observed data point to something a little bit more general. And if you think about what the problem is for network analysis, it's that, well, first I should back up a second. So what we have here is, if you go to the slides, you'll see there's this sort of train of history of where things start with. And they all have their root at this thing called a random graph. And there's an Arrow-Raney graph, Arrow-Raney random graph. And so there's everything that we're going to do ultimately is going to be some really complicated sort of variant on that. And you can get to it from slightly different ways. So I think that, we could quibble over some of my implication arrows here. But I think that the spirit of the history is, I think, hopefully right, which is that to really understand what networks are in a statistical sense, you really need to understand random graphs. And that's kind of that's the way we're going to frame it anyway. One thing to keep in mind is what we're trying to do with statistical inference in networks. And part of the problem is that when you have a network in front of you, by assumption, you have a census of the population, you have completely collected data, and it's error-free. So in some sense, everything that you care about, you've observed. A difference is a difference. There is no population inference. So like, who cares, right? So the reason we do inferential statistics in a standard setting is that you've sampled from a wider population, and you need to know if your sample differences could be reasonably generalized to the population writ large. But with the network data, by construction, you have the population. So that's not the inference question you're asking. So what question are we asking? In general, the question we're asking is the case that I have representative of a larger case of networks that are like it? That is, can I account for this case as fitting into a class of wider cases? And so, for example, I might say that the network I have looks a lot like a random network. So I think that this network has no structure to it, we made it random. If that's the case, then all of the summary statistics should be really close to what I would get if I literally went through and just flipped a coin on a bunch of edges. And I can compare that. I can ask how reasonable that's true. And you might think, well, all right, fine, you can do that, but that'd be a stupid exercise. Like, why would you do that if I care about health? And the reason you would is because, of course, you don't want to compare it to a random network, completely random network. You want to say, is this network true for would this network have been realized if people who smoke tend to hang out with other people who smoke more likely than not? That's the way to think about it. So it turns out there are classes of networks that we can fit under the like a random network rubric, but have the characteristic associations that we care about substantively. And I'm speaking in this kind of convoluted way because it really is kind of a backwards fitting. Substantively, what we're asking is, do we observe smoking homophily in our network? What that means is we test that by studying whether or not the network we observed could fit into a distribution of networks that would have been generated if that claim was true. And if we can't reject that hypothesis, we accept that this one could be from that. And so it really is a data fitting exercise. And the reason we do this, so the actual inference problem then, is from the observed single case to a broad class of cases. And we justify that by recognizing that the answers on any given day have stochastic error to them. And that the real thing we're trying to figure out is whether or not the network generation process, the data generation process, the social categories that are creating this network, whether or not that is distinguishable from simple random or otherwise stupid random issues, and instead has some kind of substantively meaningful generator built into it. And so that's the process we go through. So you have, there's a whole, I already spent more time on that than we need to. The problem, of course, is that the class of all random graphs that you might care about is a really big class. So there are billions of networks because if you think about all of the possible combinations of 1,000 nodes with 100,000 edges, that's going to create lots of different possible structures. And so this is a geometric series, and we can't possibly look at them all. And so what models do for us is instead of having to enumerate all possible networks of a given size, say, in this case, only 10 nodes, we instead say, let's look at the class of all networks with 10 nodes and 12 edges and 6 reciprocated arcs. And so that's the kind of thing we're able to constrain down. That measure ends up being much smaller. And in fact, if we can build a process that we know representatively draws from that distribution of networks, then we can get a distribution of fit statistics and compare our network to it. So that's what we end up doing. Thankfully, the random graph field is really old. It's been around for a long time, and the mathematicians have done a great job of telling us what this thing looks like. So the properties of a purely random graph, that is a graph where every edge in the network has some probability being on or some probability being off, that network, the properties of that thing are really well known. For example, we know that it has a Poisson degree distribution, and we'll know the expected number of closed cycles. We'll know the expected average path length. There's lots of things like that that we know. If you have a random network, we can then show what that looks like. Of course, in most cases, a random network isn't exactly what we really care about. There are a few features that we might care about. One of the nice things that kind of counterintuitive for new people to networks is that random graphs have this thing called a phase transition, where they go from being completely disconnected. You get a certain amount of volume. In this case, each person has on average more than one tie. You start to see a rapid increase in connectivity until by the time you get to 2 or 3, almost everybody in the network is connected to each other. This is called the phase transition to a giant connected component. And this is true of all random graphs. Now, again, you might say, well, my graph's not random. Why do I care? All graphs have a little bit of random noise to it. So even if only one tie out of the 10 ties that all your friends have or all your population members have are random, that's going to be sufficient to generate this kind of structure. And so the intuition built behind this could be quite interesting. All right. So how do we go about figuring out what is a meaningfully interesting random graph? What I like to refer to these as less random graphs. So instead of letting everything change, we let things change within categories. And so one way to do it is to say, let's say that it's a simple random graph within buckets. And so I might have a race bucket in this case. So I have white, black, and others, the 3 races I've calculated on this setting. And what I'm going to do is say that the amount of ties I find from whites to whites, from blacks to blacks, from others to others, and all in between, this is known as a mixing matrix, I'm going to say that is not random. That I fix. So I've observed 100 ties from whites to whites and 50 ties from blacks to blacks and 10 ties from others to others. I'm going to hold that to be fixed, but I'm going to let the arrangement within each of these buckets and in between the buckets, because you can fill out all 9 cells, be random. And so that's one way of making a random graph that is still random, but it's controlling for the thing you care about. So if I think that the observed process is built entirely on race homophily, then my network should look the same because everything else is random. And when you do that, you find that it doesn't. So this is what the real world looks like. This is what the random world would look like. They match exactly in terms of this mixing matrix over here, so the proportion of ties in each one. But just by eyeballing it, you can tell that the random network is much more diffuse. There's much more overlap. There's lots of other sort of diffuse connections going on that you don't see here. And so what that tells us is that there's something structuring this network above and beyond the simple race mixing. And so it's our job to figure out what that something is. And so we can do that in lots of different ways. For one thing, we can see that the degree distributions don't match. So we find that in the real network, there are more people with a small number of ties and a few people out here with really, really high number of ties. Whereas in a random graph, you get this almost normal distribution because a Poisson distribution converges on normal when the degree is high. And there's lots of ways you can do this, and you can think about what these things look like. And what a lot of the work that's done in generating statistical tests for networks is to figure out how to constrain that randomness. Now, there's another way to think about randomness in networks, and this is to think about a random association process. So if we think about our little race mixing example, you could think of that as an edge list where I have person 1, person 2, race of person 1, race of person 2. And so you think about that kind of a simple edge list. Well, I could ask, if I were to randomly sort the races across that edge list, would I get the same thing? That would be another way of doing a mixing matrix where you're holding constant the number of people of each race, for example, in this little case I'm making up on the fly. But you're randomizing the association between race and ties. The formal way to do that is called a quadratic assignment procedure, or some other kind of what's known as a permutation test. You compare an observed bit of the world to that same bit of the world where you deliberately randomize some element. And by deliberately randomizing it, what you're doing is you're mechanically breaking any association between the network structure and the thing that you're randomizing. And so if my question is, does marriage predict business if you're in, 14th century, 15th century Italy, it turns out that I get the question, the equivalent question is the association between marriage and business the same as I would have observed if it had been random? And you can do that with what's called a QAP test. I can correlate these things. We see in this particular case, the observed correlation is 0.37. If I do a lot of random mixing of those two things and do it, you never get a correlation that high. So here you see that this distribution is the correlation you would expect to see. It's centered on 0, but it's clumpy because of the underlying structure of the network is not big enough. It's a small network, so you get up with this kind of clumpy distribution. But you almost never observe as high a correlation as we observe in real life. And so what that tells us is we don't know what causes this association from this test alone, but we can tell you that it certainly wasn't driven by random. Now, again, you say, oh, Moody, random's a stupid model. And I agree with you, but we could say random controlling for or random within other things. So say given age distributions or wealth or what have you, you can do these permutation tests in a multiple regression sort of way where you're controlling for the other things. It's not exactly this, but effectively what you're doing then is you're randomizing within while holding those associations constant. Is that all clear thus far? Someone stop me, because I will, like I said, once you get me talking, I keep going. All right, so the second thing then is to think about that the QAP model is, and the other kind of permutation models are probably the simplest out-of-the-box way to test whether or not there's whether or not there's enough smoke in your situation to suggest fire. And so if you do a permutation test and you discover that there's a high probability that your association can't be accounted for by a smart version of randomness, that tells you that there's probably a real social process that's driving it. Is it a pure test? Is it a good causal estimate? Probably not. But it will at least help you think through what would get you to that. What you're doing in that case is you're modeling an outcome as a function of the network. What most of the interest in network statistical modeling has been for the last, essentially for the last 15 years, has been in modeling the network itself. And the idea here is to say, can we account for what drives this network? Where does this network come from? And to do that, we take this variant of an Arrow random graph, and we keep constraining it until we've reached to a point where we fit the network. And then we can effectively say that this series of constraints are enough to account for the network. And so we fit the network. For those of you that are used to hypothesis testing rubrics, you'll probably recognize that there's a bit of slippage between fitting a network and testing an association, because it could be that some other thing that you've not observed correlates in the aggregate with all the other things simultaneously to create a predicted value that could get you to the same place. That is, the simple way to think of this is that there's lots of 2-digit combinations that would both add to 10, right? And so I have a 10 in front of me. I have a certain set of 2 digits that added to 10. I can't be certain that it was 2 and 8, but I can be certain that it wasn't 2 and 9, right? And so that's what the logic going on here is. You're giving it a series of digits that you think fit the network you've observed. You've observed one, you're going to add that series of digits to it, and you're going to see which is there. It turns out, of course, that networks are big and they're complicated, and the kinds of things you fit are extensive enough that you're unlikely to have a 2-digit adding to 10 kind of problem, but that's the logic that we're doing. Does that make sense? All right, so what does that actually look like? I've found this little example, I think, useful. Hopefully you will. the way it works is to imagine your data matrix as an adjacency matrix, and that's what this little blue, red, and gray thing is in front of you. And the adjacency matrix is a data point. It's either is 0 or 1. And so in this case, the red ties are the red cells are the observed ties. So we see that person 1 is tied to person 3. Person 3 is tied to person 4 and 6, for example. We see that person 6 has 1, 2, 3, 4 ties, right? So the in degree of person 6 is 4. Like that's just your basic adjacency matrix. And one way to think about what this is to recognize that, well, what you have in front of you is trying to model a series of zeros and ones. We've been modeling zeros and ones for years with logits. And so we could just run a logistic regression on the dyads and say, let's model whether this is a 0 or a 1 and call that good, and see how that works. Your instincts say that that can't work, that couldn't be right, but put that aside for a minute and we'll come back and see what it brings us. So one way to do it is to say, let's just fit a logit model that has one parameter, just an intercept. If I were to do that and fit a logit model that said that Yij, which is what this thing, is equal to whatever this intercept model is, what that would effectively say is that every cell in this network is equally probable, right? So whether it's a 1 or whether it's a 0 in reality, and that's the bold ones are 1s in reality and the others are 0s in reality, the predicted probability is the same. And that's as it should be. And so if I have a 1 parameter model, that means that everything has to be the same as a constant. And what that is a density estimator. And so that's telling us that the probability of a tie between I and J on the logit scale is minus 1.13. If you exponentiate that, it comes out to saying that the density of this network is 0.24. And so that means that overall, you have potentially a 1 in 4 chance of there being a tie in this network, but you haven't learned anything about it, right? So this is just a model-based way to get you to that original Erdos-Randi graph, and that's exactly what this is. So a 1 parameter ergom model, exponential random graph model, is just a logit model that has a single constant on the right-hand side of the equation, just an intercept, and all it's doing is telling you that everything is equally likely. You wouldn't fit that model, it's a stupid model, but that's the starting point. You build from there. So if you have that model, you could say, well, I know that some people have more ties than others. They're just more gregarious. And so I could add a row effect to this model. I could say that each sender has a different probability of sending a tie. And so each of these people in the darker blue, like they each send 1 tie. So they have essentially a 0.13 chance of reaching anyone else in the network. There's no way to distinguish them. And as you'll see from this little figure here, all the rows are the same. And so this is a row conditional model. And it says that people differ in how gregarious they are, but it tells you nothing about who they might send a tie to. It just says that this person in the middle, person 5, is going to be the most active. Now, you can probably see what's going to happen. If I can have a model for the out degree, why not have a model for the in degree, right? And so I can say that there are target effects. And so these 3 people are really likely to be targets, right? Whereas these 4 people are really unlikely to be targets. And that's just, again, the exact same model. And you've done it with this kind of a modeling framework. You literally just fit a probability model to a space. Now, in most cases, what you might want to do is take the joint of that. Now, notice what's happened here, right? We have only 3 parameters in this model. We have a baseline intercept, so that tells us the overall density of the network. We have a difference for the number of ties some people send and a difference for the number of ties some people receive. And as you might expect, people who send a lot of ties tend to send those ties to people who receive lots of ties, right? So we hit here, we got a red value, that's a predicted value probability of 0.84 in this case, on a case that is also a 1. So we're getting a lot of good fit here. We're matching where we should match in place, and we're seeing almost no ties over here, which is also true. So the simplest possible model in this case is doing a pretty good job, and that's because this network is pretty simple, and the degrees are doing a good job capturing what's there. Now you could stop there and say, well, this is just clearly an effect of the ties going on. But you'll notice that there are some mistakes, right? So we're saying that these 0.27 ties here have a very low probability based on this simple marginal model, but they were observed. This tie has a pretty high probability, but wasn't observed. This tie has a high probability, wasn't observed. So the model misses in some weird sorts of ways. It would be nice to figure out what that is. And to fix that, we add these things called dyadic similarity coefficients of some sort. So these might be a homophily, both smoke, both in the same grade, something like that. And so at this point now, we're risking overfitting the model, right? So we have a 0.99 probability of matching on these things. And so that means we're really certain that these ties are there. And we're really uncertain that some of these other ties are there. But this is the point of the model, is that with a simple volume out and a simple volume in and some information on something like homophily, you can often get pretty close in these types of networks. And that's the logic of an ergom model, of an exponential random graph model, is that it really does a nice job. You're still going to miss. The world does have random elements, and your model might be misspecified, but that's how the model works. The idea is you can keep building in different coefficients. What I've called here dyadic similarity, you might actually have a race homophily, a sex homophily, a SES homophily, like lots of different characteristics. It might also be that we expect friends of friends to be friends with each other, and so we might have some kind of a triadic effect or something like that. But the logic of the model ends up being exactly the same. And what it's doing is it's using the logit not in the way that you would expect to use a logit. It's not using a logit because you're really interested in estimating a coefficient directly. Instead, what you're interested in doing is getting a probability model. And so an Erdos-Randi graph, the original random graph, is just a probability model. It says each of these cells has a fixed probability. They're all the same. And what you want to do is get a slightly more complicated probability model, and that's what an ergom does. It allows you to get a conditional probability model where the conditions are features of either the nodes or the edges of the graph. All right. So a key element to keep in mind in the interpretation of this is I've spoken about it as if it were a logit on the dyads, but in fact, what it is a model for the network as a whole. What this equation is doing right here is it's defining a class of networks. And so if I were to take these probability cells, flip a coin proportional to it, all of those observed networks would be equivalent in the sense that they are members of this class of networks that are defined by this equation. And what you're doing when you're testing a statistical model of a network, or you're trying to fit the network, is you're asking, is the network that I have in my hand, is the network I've observed, a reasonable fit to the class of models described by this equation? And the reasonableness of that fit is a tricky thing to capture. And we have these things called goodness of fit indices, but that's the logic of the process that you're trying to do. All right. And this is just the model that I just talked through. So how do you get here when you're done? What you'd like to, typically what happens when you do a model, I'll use this as my example back and forth, is that you have many more of these dyadic similarity features than you have than just a single one, and they rarely fit as well as they do in this little toy simulation. Instead, you are trying to guess, like, does race matter? Does sex matter? Does SES matter? Does smoking matter? So I have all of these things in the model, and I put them in, and I'm going to get a number, and I want to know if that number is bigger than I'd expect or not. And so that's typically a statistical, that's a statistical inference question. And we solve that statistical inference question with these exponential random graph models. And so what they've done under the hood is figure out not just what that coefficient is, but how different that coefficient is from a simple random coefficient. So in this sense, it's very much a like any of your standard statistical inference problems where you're trying to see whether or not the coefficient is statistically significant. And what a statistically significant coefficient means is that the likelihood of your graph fitting this class of graph depends most on this coefficient. This coefficient is different from 0. And you can take the others out. So it has that nice model fitting feature. And so the process then of fitting these kinds of models, and I'm using ergoms as the baseline example, there's other classes of models, but they all have the same kind of logic, is that you come up from your theory some specification for the model, test it against it, and then you examine through this iteration process, this MC-MC chain process, this MC-MC process, the chain is redundant. for convergence to see whether or not your graph fits it. And if it doesn't, you have to adjust the model. You have to go back and find something else that fits. And if it does, you publish your paper and go on to fame. Now, when I say specify the model, the question is, what do you specify it with? And so the kinds of things we typically use are the ones that we can get off the shelf from the StatNet team, or some of the, there's a couple of the tools now. There's a political science one, and there's one hand user one. But the one we're going to use in this class is coming from the StatNet development team. And what they've done is they've pre-computed for you a series of statistics that you can fit to the model. You can think of these as equivalents to those row, column, and dyad effects. They all have that kind of flavor to them. And these typically have, these are of two broad categories. One of these categories are called dyad independent. The other are dyad dependent. And dyad independent are features of the network that don't depend on two people simultaneously. And so these are all your row effects, all your column effects, surprisingly, all your homophily effects. So the thing about the reason homophily doesn't depend on any two characteristics is it depends on the intersection of all people in those characteristics. And so it's a class feature, it's a block as opposed to a dyad feature. And so for those features, it turns out through some math that we're not going to go into today, but through some really fortunate features, that those things are in fact not just well estimated in terms of the coefficient from a logit model, they're accurately estimated using the standard off-the-shelf logit maximum likelihood estimation for the standard error. Or if you really want to be accurate, you're not going to do any better for a standard error than you would if you were to use a more complicated estimation routine for the standard error. So it's as good as you're going to get. It's the best. It might not be completely unbiased, but it's a good estimate. And so these are known as dyad independence models, and they're fit really well and really fast with all of these kinds of tools. The thing about them is that they're really good at answering the kinds of health questions we care about. It turns out that often the things that health behavior scientists are most interested in are homophily measures or variants of homophily measures. So we want to know whether or not two people with the same characteristic are more likely to be tied than two people with different characteristics. And those characteristics could be smoking, could be using drugs, it could be being obese, right? There's all kinds of things that generate that are health features, or it could be some other attribute like a status characteristic. But at the end of the day, the model doesn't care. They're all dyadic independent features. And so that's what they make them really nice and clean to fit. Now, one of the problems, though, is that social networks, even though we're only interested in the easy to fit features, the other features are still confounding the estimation. And so if the social thing going on in your network is being generated by homophily and transitivity, for example, if it's the case that we expect friends and friends to be friends, then that's going to create a contamination that's going to bias some of the other features. And if you don't account for that contamination, then you're going to have a model misspecification and thus model misspecification error and a biased result. And so you have to somehow account for these kinds of non-dyadic independent features. And that's where really all the work of estimation in these models has been put. It turns out it's really difficult to estimate those for lots of different reasons, not the least of which is that the models can be a little bit finicky in terms of how you specify them. But the kinds of features you can add are lots of things that have to do with transitivity and so forth. Now, when I say the models are sensitive and hard to fit sometimes, this falls under a category of problems known as model degeneracy. And for about 10 years, this was a really kind of a black eye on the modeling people. In fact, people who are used to doing general linear models, like all of us learned in graduate school, would take a network, they'd run it through an ergon model, and the result would be nonsensical. And they'd say, well, this model must be bad. There's something wrong with ergons. It turns out that, as every programmer knows, computers just do exactly what you ask them to do. And the problem with us as social scientists is that we've gotten really spoiled dealing with linear regression in the standard independence case, because standard linear regression is really robust to model misspecification. So if I think that the effect of the things driving obesity are your income and your education level, and I don't include an interaction term between income and education, probably not going to matter much. It might matter a little, like you might get a tiny little bit of error, but it's not going to be wildly wrong. Because these models, because the non-independence features are effectively simulating a network and building that network from the social process you're specifying, it really depends on what you're specifying. And transitivity is the classic example of this. So if you think that a friend of a friend should be a friend, then what you think about that from your intuition based on regression, on standard linear regression, is that if I have a few friends, then there should be a few close triangles. If I have a lot of close triangles and I have a higher probability of tie, it should be some kind of a linear relationship. And that would make perfect sense. Like you think of this as income and education or something. This is the way you would expect this model to fit. And if it's curved a little bit or whatever, it doesn't really matter. But in the network sense, the problem is if this thing on the left is good, if you have a more close triads than you'd expect by chance, but not complete, the model is saying that if you give me a linear positive correlation, what that's telling the computer is that if this is good, this is better. And so what it's going to do is it's going to say, there's an open triad, close it. And that closed triad might create a bunch of other open triads, quickly close those. And so what it's doing is it's taking as meaningful throughout the range of all possible combinations the linearness of the specification you've given it in the model. And what that's taught us is that, in fact, it's not the case that friends of friends should be friends. It's that my closest friends of friends should be friends. But my 100th friend, I don't care if they're friends with somebody else. There's diminishing marginal returns to the number of closed triads you see in a network. And this is a constraint, a human constraint, that's based on the fact that we don't have time to be friends with all of our friends, right? We have to be selective, and that closes in the ties we have. And that means that networks are not actually fully transitive, they're partially transitive. And that partially transitivity creates this diminishing marginal return. And so what this has taught us is that networks, these kind of network generation models, of which Ergomis is the archetype of the class, they have that's the way to put this, a reality to the model specification that is much more exact than our intuition would normally be. And because we don't think well in combinatorics, we're used to sort of imagining the world down here in the realm of 20 or 30 closed triads, which is what exists in the world we walk around in. But in a network of 100 people, you can have thousands and thousands of closed triads. And so the computer doesn't know the difference between linear here and nonlinear here unless you tell it to do so. And so that's what we've learned over the time. So things like model degeneracy, and there are other features that can do this, are features that say you have to specify the data generation mechanism appropriately and in a way that applies over the range of all possible values for the independent variables, in this case, closed triangles. So that's the world's fastest introduction to logit models. Once you understand the logit model, which is this constraining of the ergo model, which is this constraining of the probability space, you can generalize that in really interesting ways. And perhaps one of the most profitable, sort of intellectually profitable ways of generalizing is this class of models known as latent space models. And so what latent space models do is they take the same model we had before, a logit model. This is just a different way of writing a logit model. And they add to it not just your observed statistics that you might have, but a couple of other statistics, this ZI and this ZJ. These things are unobserved, that's why they call it latent variables, that define a social space. And so if you imagine a simple XY axis, I probably have a picture here, there we go. If this is the observed network, what the latent space does, it says this might be Z1, this might be Z2, and we would expect to find a tie where people are close to each other. And that's what we would expect intuitively. So how about we just invent a space that makes that true? So that's what a latent space model does. It says, I don't know what Z1 and ZI and ZJ might be. Like whatever this space is some distance between, it creates a distance between us in some imaginary social space. And I'm going to construct that imaginary social space in such a way that people who are near each other in the imaginary social space are more likely to be tied than people who are far away. And what's nice about that is it allows you to get a pretty good fit of your network, even if you're ignorant of a lot of the things that social processes that might be generating it. So I might not really understand the 5-node version of a friend should be a friend. Like there might be a pentatonic version of that I don't understand. But if I'm doing an ergom, I have to be able to specify that. That should be part of the model, otherwise I'm going to get it wrong. What the latent space model says is, I don't know why we're close. It might be close because we have friends in common. It might be close because we're genetically similar. It might be close because we both like koi fish, right? There's 1,000 things it could be. Who the hell knows? But I'm going to just fix it and make it true. And then you as the analyst can add in the other things that you think might matter, and we've already controlled the way for all that other stuff. So the beauty of the latent space model is that they're really robust to investigator ignorance. So that all the things we don't know about our settings that are driving relationships, we're going to shove into this latent space. The advantage of that is that it controls for it. It holds it constant, and then you can test the things that you've observed that you care about. The difficulty is that you're essentially letting your model be driven by your ignorance. So if you really don't know what it is, and that's taking up the largest feature there, that's intellectually can be a bit dissatisfying if you don't know what's there. Turns out the models are pretty easy to fit. If you go through the labs, you'll see how to do this. It really is just this, a single line in the latent space code, the ergom M code, and it works out really nicely. Graphics that come with it are nice. You can also apply versions of this latent space that say the latent space isn't constant across the population, but effectively you can have sub-latent spaces. You can put groups over the latent spaces, which make it much more flexible and allow for heterogeneity in the extent to which distance in the latent space affects the likelihood of a tie. So you can collect a lot of things here that make it nice. The Uber version of this is a set of models called Additive and Multiplicative Effect Models, developed by Peter Hoff and Alex Polfosky, both here at Duke. And these models do the exact same thing we talked about before. This is organized a little different than that program I showed you before with the little matrix, but essentially these are sender effects, receiver effects, diet-specific effects, and then a whole series of error effects that you can build into a latent space. And that's what this little projection thing down here in matrix space looks like. But this projection thing is the latent space. And what's nice about these models, it allows you a whole array of different kinds of specifications for these models. And Alex will speak a little bit about them tomorrow in his new version of these models, which adds a different term, which is the cohesive subgroup that you're, the community that you're a member of. And so all of these coefficients then get conditional on that set. These are fully multiplicative in that sense. So all of this is the way, you didn't understand that. I barely understand it. I appreciate that. That's not what I just wanted to put this out there as something that you have a chance to go look up if you're interested in. The main thing about the AMAN package is it's a well-documented package that works well. It is a little slow. It doesn't work on really large giant networks. So if you have a giant network, you don't want to use this. But it does provide a lot of opportunities to fit models for other reasons besides networks. And I'm going to stop there and answer questions. Is that too much too fast? Anyone? Paul, did I get it basically right? Any other questions, things you want to add? Hold on, might not be listening. Okay, come on.
I'm sorry. Could you say again why, and this is probably dumb, but why homophily is considered dyad independent?
Yeah, that's a really good question. It's because our intuition is that it should be dyad dependent because it's affecting two people being the same. It's not, because the right way to think about homophily is that what it's doing to the adjacency matrix is creating sub-adjacency matrix. And within those subgroups, the networks are essentially little random graphs. It creates a block diagonal graph around same race, same sex, same age. And so you have this whole collection of people that are all shared, and it's not dependent on any single individual. Does that help? Okay, great, yeah. And it really is, it's just a, there's a whole theorem built around, there's these things called graph dependence models that are under the hood here. That again, I'm starting to get out of my depth on, but these are, you can reproject in the parameter space the extent to which parameters depend on other people's parameters. And it just turns out that the homophily ones do not, which is really convenient. It's also, by the way, just as long as I'm riffing, the thing that makes it possible to generalize from an ego network to a global network. All those dyadic independent features are the same things that make it possible to simulate a global network from a local network, because you're doing it with all of those homophily and degree features. And so it turns out that because they're dyadic independent, they're also randomly sampleable. And so if they're sampleable, you can then generalize from them. And that is, again, another feature that's great. Now, it turns out once you get that architecture in place, you can also simulate, if you happen to have the information like closed triads within the ego networks, you can do some of those features in the simulation side from ego networks as well. But it's really easy to simulate from the homophily parameters as well. So effectively what you have is a complicated stochastic block model. You can imagine, if I had 3 features, if I have, race, sex, and gender, sorry, race, sex, and age, then effectively what I have is, a big block of people that are the same race nested in that, people that are the same gender nested within that, people that are the same age. And so the diagonal set of that big adjacency matrix are all equal probabilities. It doesn't matter if there's 10 people in that cell or 100 people in that cell. So the other thing that I didn't I went over really quickly there, is I did the QAP model is the only thing I discussed in this set on ways of testing the association between a network structure and an outcome. And so these network outcome association models are known as peer influence models. And we're going to talk more about those tomorrow, particularly in the context of the Sienna models. The day is going to be a little bit mixed around tomorrow because of people's schedules. We just had to work it out this way. And so the Sienna models, we're going to do advances on Sienna models in the morning. So it's going to be the first thing we do. So it's going to be jumping in deep when the morning first starts. But the main thing about Sienna models are what they're trying to do is to fit the ergom on the one hand. So they're trying to figure out what's driving the network. And it turns out that one of the things that's often driving the network is, say, your dependent variable. So if I care about smoking, which is the classic example, it's probably the case that people who smoke are likely to be friends, but it's also the case that people who are friends, if one of them starts to smoke, the other one's likely to become a smoker. So if I'm trying to predict who's going to smoke as a function of peer influence in smoking, I need to account for the fact that there's a selection feature into smoking and a selection feature into being in the same network. And so what the Sienna model does is it effectively combines the QAP model and the ergom model into one simulation model. It's not actually a permutation test, it's a different kind of simulation, but you can think of it intuitively as the two things working in tandem. And so on the one hand, you have an ergom model that's under the hood that's creating the likelihood of a tie. It then simulates and randomizes a permutation test kind of thing for who smokes. It then readjusts the logit coefficients, it then readjusts who smoke. It does this back and forth in the simulation process to align the best probabilities of both of these things happen simultaneously to fit the data. Just like the ergom models, it's the same kind of fitting exercise. So you come up with an equation that matches the data you've observed. There might be a different equation that would also match, but that's the process you're engaged in. Does that make sense? And what's nice about these models is just like the ergoms and the latent space models, is that these have now all been generalized to almost every other kind of data that we have. So they were originally invented just for binary. Ergoms are always directed. That was the easier case actually than the undirected. But so you have binary, but you have binary directed, undirected, valued, one mode, two mode, dynamic, static, and it's really gotten to the case now. There's also a new multi-layer version of them that are coming out. So the class of types of networks to which these models now apply is growing dramatically. And what we're going to hear tomorrow morning is, or you hopefully have a chance, if you haven't seen the video yet, to go check out, is both David and Cassie have done different work on essentially variants of the base Sienna model. So the baseline Sienna model is a single behavior on a one mode network, usually a binary network, and over multiple time waves. And what they're showing is ways to do it in which the temporal space is uneven, so there's temporal heterogeneity, or where the network type is a two mode, it's a person's two groups kind of network. And so it's a really nice advance on both of these products. Other questions or thoughts? You can just talk at a stream. All right, let's take 5 minutes then, and then we'll come back for those that are interested, and I can give a quick overview on some visualization ideas, and then we'll wrap up the day.